You ever look at a weld, you know, that shimmering line that holds two huge pieces of metal together, and just wonder, how does that actually work? What's the secret sauce that gives it that incredible strength? Well, today, we're going to go behind the torch and explore the invisible science that makes these joints so powerful. But here's the thing, there's a catch. For as strong as welds are, they're often considered the weakest link in any structure. Kind of weird, right? I mean, you're literally fusing metal with more metal. Shouldn't that make it just as strong as the original pieces, if not stronger? Well, the reason for that little paradox all comes down to things happening at a scale you just can't see. The secret to a weld's ultimate strength, or its surprising weakness, is all happening at the microscopic, even atomic level. I mean, think about what welding really is for a second. You're taking solid metal, blasting it with intense heat until it melts, letting it all flow together, and then hoping it freezes back into something strong. That process, that controlled destruction and rebirth, it completely scrambles the metal's original carefully designed internal structure. If you're not super precise, you're basically building a weak spot right into your design. So how do engineers get around this problem? How do they fight back against this built-in weakness? Well, they call in some microscopic heroes. We're talking about these incredibly tiny particles called precipitates. And these little guys are the absolute key to turning a potentially weak seam into a bond that can be even stronger than the metal it's holding together. So what in the world is a precipitate? Okay, the best way to think about them is like microscopic rebar, or maybe thousands of tiny little anchors scattered inside the metal's crystal grid. When that metal is put under stress and tries to bend or warp, these little particles physically get in the way. They block that internal movement, making the whole material way, way stronger and harder. They literally lock the atomic structure in place. And, you know, this isn't a one-size-fits-all kind of deal. Different metal combinations, different alloys, they create a whole cast of different precipitates. So in the aluminum alloys you see in bikes or cars, you get these magnesium and zinc particles. In magnesium alloys, something totally different. Each one is like a unique recipe, designed to do a very specific job inside its host metal. Now, the first big lever that engineers can pull to get these precipitates just right is heat. The energy from the welding process itself is this double-edged sword that can either forge amazing strength or create some serious weakness. It is a serious balancing act. What you really want is a lower, more controlled heat. That helps those perfect fine precipitates to form, and it refines the whole internal structure. In fact, some research shows that when you optimize this with something like low-heat laser welding, you can get joint efficiencies up to 93%. That means the seam is nearly as strong as the original metal, which is a massive deal for safety-critical parts. But if you crank that heat up too high, you get these clunky, brittle compounds that actually make the welds softer and weaker. But heat is only half the story. The second and just as crucial piece of the puzzle is chemistry. You've got to start with the right ingredients if you're going to cook up a strong bond. And this is where things get really clever. Engineers can add a super thin layer of a different metal like copper that mixes into the aluminum during the weld and creates brand new strengthening particles on the fly. Or, get this, they can add things like titanium carbide nanoparticles into the filler wire itself. These nanoparticles act like seeds, encouraging a much finer and therefore stronger grain structure to form as the weld cools. It's all about engineering that perfect chemical recipe for strength. So you might think, okay, the weld is done. It's cooled down, job's finished. But that's actually where some of the most amazing strengthening can begin. These post-weld treatments are kind of like the secret sauce, that third and final lever you pull to unlock a joint's absolute peak performance. Just take a look at this wild case study. So after welding a joint, researchers first gave it a gentle heat treatment, a process they call aging. And then they did something pretty extreme. They dunked the entire joint in liquid nitrogen, freezing it solid to minus 190 degrees Celsius. And they just left it there for a full 24 hours. And the result of that deep freeze? A mind-blowing 54% increase in the joint's strength. That extreme cold literally forces even more of those tiny, powerful precipitates to pop into existence inside the metal, beefing up the weld zone like crazy. An increase like that is huge. It could be the difference between a part on an airplane wing failing or lasting for decades. It just shows how powerful this aftercare can be. But you don't always have to resort to things like liquid nitrogen. Sometimes the only ingredient you really need is time. There's this phenomenon called natural aging, and as this quote points out, Sometimes just letting a certain type of aluminum weld sit around at room temperature is enough for those precipitates to form all on their own. You can see it right here on the chart. The day after welding, the hardness is at a certain level, but then you just wait. After 8 weeks, the hardness has shot up significantly, and it's all thanks to those precipitates slowly but surely locking the microstructure into a stronger and stronger state. The metal is literally strengthening itself over time. So the takeaway here is pretty simple, but it's also really profound. The massive visible strength of a bridge, or a car, or a skyscraper, all of that depends on our ability to control these completely invisible processes. By perfectly managing the heat, the chemistry, and the aftercare, we can engineer strength from the bottom up, right at the microscopic level. And look, these ideas aren't just for old-school welding torches. These exact same principles are being used right now in the most cutting-edge technologies. Everything from super precise laser welding to the additive manufacturing that's totally changing how we build things. Which kind of leaves us with one last big thought. We've gotten really good at controlling materials at the micro level. So what's next? Well, it's got to be the atomic level. As we move forward with things like 3D printing, you have to wonder, how will we learn to engineer materials by placing every single atom exactly where we want it to create things with properties we can barely even imagine today?